Hello, hello, hello. Welcome, welcome, welcome. I'm Nick. I'm here to walk you through CS50, Harvard Artificial Intelligence Project 4.1, 4.x. There's two of them. And good news, this one is super easy. And I'll get rid of myself here. But in this project, we're going to use artificial intelligence to peer into the behavior of online shoppers and predict whether a visitor is going to make a purchase or not. Our job is pretty simple and pretty powerful. So we're going to feed a machine learning model real user session data and teach it to guess whether somebody is going to buy or not buy. By the end, you'll see how to build a classifier that doesn't just randomly guess, but instead it makes an informed, trained decision based on meaningful insights. So let's look at what we're going to build. Really, it's just three functions. Here, there's load data. So this is our bridge into the raw CSV file, which we'll get into in a minute. And this is the bridge into our artificial intelligence so it can learn from it. It'll parse each row and convert the fields into numeric evidence and also extract a label. So essentially evidence and label for each row. Next, train model. This takes the evidence and feeds it into the k-nearest neighbor classifier. And this is where the artificial intelligence model actually learns patterns in the shopper's behavior based on the training data that we feed to it. And finally, evaluate. This is going to measure how well our machine learning model performs. And we're going to use sensitivity and specificity. I've opened the page for the k-neighbors classifier from scikit-learn, which is the one we're using. And for this project, we're going to be concerned with this parameter, the number of neighbors. We're going to be concerned with the fit function. And then we're going to be concerned with the predict function. So let's jump into the project and have a look. Let's get that project open. I've just downloaded it. I've just opened a fresh copy right now in VS Code. There's just two files, shopping.py and shopping.csv. And for your students, if you teach this class, I would recommend to do kind of a little tour of these files and figure out a good order to rebuild the project once you've already built it. So let's take a look at what we're using here. Scikit-learn, sklearn. We're using this train test split and k-neighbors classifier. There's a main function. The main function takes an argument, which we can kind of see from this sanity check. That argument is going to be the name of this file, shopping.csv. This shopping.csv is our data. Each row, except for the first one is the name of the columns, but it's kind of broken into two pieces. The evidence, which is everything before the last Boolean, and that last Boolean is named revenue. So we're kind of true or false, did they buy, didn't they buy? And that's what we're trying to predict. We're trying to predict, given all of this evidence on a unknown customer, are they going to buy or not buy? So you can think of each line as split in half between everything left of the last Boolean and then to the right of the last Boolean. And that's what load data is going to do. This is essentially a parse job, and it tells us right here exactly how to parse it. And it's ultimately returning a tuple, which it says right here, return a tuple, evidence labels. And evidence is going to be a list of lists, and then labels is going to be a list of 1 or 0 with the same number of elements as the outer array of evidence. So we could already kind of set that up to return. So return evidence labels, and then they're just going to be lists. So evidence is a list, and then labels is a list. Those both mean list. Train models, or train model, given a list of evidence lists and a list of labels, return a fitted k-neighbor model with k equals 1 trained on the data. So we can just knock this one out. There isn't that much typing, but this is really the crux of the project. So what we're going to do here is make a model, which is going to be exactly this one, the k-neighbors classifier. And then we're going to do something with it, and then we're going to return it. And it says right there we need k equal to 1. So k is n neighbors 1. And all we have to do is fit it. So I'm just going to say model.fit. And the arguments here are going to be kind of in this format. So something like 1, 2, 1. And that might be kind of hard to read, but it's a 2D array and then a 1D array. And that's what we're feeding into this function, evidence and labels. Evaluate is going to be returning a tuple sensitivity specificity. So we can just kind of do that, return a tuple sensitivity specificity. And for now, I'll just set these to none. And that's really it. That's going to kind of be the structure of our program. So how do we build this evidence and labels? Well, let's roll up our sleeves. So let's use the CSV to parse our data. And we're lucky he gave us everything we needed right here. So this tells us exactly what to do to get to the end. So let's bang it out right now, ASAP, no questions asked. So let's go, let's go, let's go. I'm going to open that file name. That's our only argument here. So with open file name as file. We will get a CSV reader. I'll just call that reader equals csv.reader, taking that file as an argument. And then we want to skip the row of column names. I've got a comment for that. We can just do next on reader. And then we can loop through what's left. And I'll just do this with row. So for example, for row in reader, something. And that something is going to be making two things. Something to add to our evidence, something to add to our labels. So I'm going to call it evidence row is a list, and then label is an integer. I'll just set it to 0. And at the end of this loop, we're going to say evidence.append evidence row and labels.append label. As such. So how do we translate all of these comments into us coding something? Well, let's take a look at the comments I made here, and it will shed some light. Kaboom. So it may seem daunting or tedious, but really it's not. This one is a integer and administrative. We don't need to worry about the name, but just the index. So for example, I will add to evidence row with append some integer. We're casting a string to an integer, so that'll be row 0. And then administrative duration. This is a float, so we can do like evidence row.append float row 1. So here are the rest of our rows up to special day 10, the month. I'm going to use month lookup table, but I'll just show you real quick what it does. In shopping.csv, we have stuff like Feb as a month. An interesting one to note is June, June. I've just gone through and figured out what each one of those were and created this lookup table. I won't bother retyping it, but as you can see, it maps each short month string to an integer, like January is 0 up through December is 11. So then using that, we can say like month equals month lut of row 10, and then evidence row dot append month. Then up to 14 are all integers. I'll just do the copy pasta here. Boom. Visitor type. These are in this format: returning visitor, new visitor, and there's a third one too. But I've made a lookup table for those as well. So I'm just going to paste it in here. You may have some creative tricks, something else to get these values. This is just how I've chosen to do it. So using visitor lut, we can, for index 15, we can say visitor equals visitor lut for row 15, and then evidence row dot append visitor. Then weekend and revenue. Revenue is the important one, that's the label. But these are both true, false, and there might even be a smarter way to do this. But what I've done is I've made a Boolean LUT. So it just maps true to 1 and false to 0. So I will say weekend equals Boolean LUT of row of 16, and then evidence row dot append weekend. And revenue is the label. So this is the special one, but it doesn't look that different from anything else we've done. So I will just say label equals Boolean LUT of row 17. And beautiful. So the bang bang boogie and the boogie don't stop. No, it doesn't. No, it doesn't stop. All right, evaluate. How are we going to do this? Well, it pretty much gives us exactly what these values need to be. Sensitivity should be a floating point value from 0 to 1, representing the true positive rate, the proportion of actual positive labels that were accurately identified. So I'm just going to add a little comment here. Correctly predicted positives divided by the actual number of positives. And then for specificity, it is the correctly predicted negatives divided by the actual number of negatives. And those will both be between 0 and 1. So how do we get these things like the actual positives and the predicted correctly positives? Well, it's pretty easy. I've chosen to use some fancy Python wizardry to make it more impressive perhaps than it really is. But if you're a wizard like me, then you're gonna love it. So I'm also a big safety freak, so I want to be really safe. I'm going to say the count equals the min of the length of the labels and the length of predictions, just in case someone gave us different sizes. All right, so how do we count actual positives? Well, I'm going to name it actual positive count. And this is just the number of labels that are true. So a fancy way to do that is the sum 1 for I in range of count, where the label is true. So if labels I, and then the actual negative count can just be the total count minus the actual positive count. And then the true positives is going to be the number of indexes where labels is true and predictions is true. So we can use some of that stuff we learned at wizard school, the sum 1 in I, 1 for I in range up to count. Again, where labels is true and predictions is true, or where labels is 1 and predictions is 1. So if labels I and predictions I. And then true negatives is going to be similar, the sum 1 for I in range of count. This is if labels is 0 and predictions is 0. We can just say if not labels I and not predictions I. And in the spirit of staying a safety freak, I'm worried about divide by 0. So we're dividing by the actual positives. So I'm just going to say if actual positive count is greater than 0, so just if it is truthy, then sensitivity is going to be the true positives divided by the actual positive count. And the actual number of negatives we have as a denominator. So I again am going to check the truthiness. If it's not 0, then the specificity is going to be true negatives divided by actual negatives. And we should be able to run it and gun it. So I'm just going to run it and gun it. And that's what our program does. Nothing. It prints these two things, the true positive rate and the true negative rate. As we can see, it's really good at predicting when somebody's not going to buy something. So awesome. Give it a thumbs up and tell your buddy about it. AI. It's real.